I use your measure of variance, and then I do the remainder of the calculations. So if you give me the correct mean, you got the variance wrong, I use whatever your wrong estimate of the variance is to figure out whether you got the correct measure for standard deviation, standard error, confidence interval, and the confidence interval. So anytime somebody gets something wrong, I have to recalculate everything on the basis of what the wrong answer was, and that ends up being time consuming. It ends up being time consuming the more people who miss one of the steps. But you can get this wrong, or get this right, get this wrong, and get everything else correct, assuming that you do the remainder of the calculations correct based on that initial incorrect variance estimate. So that's a little time consuming. Same thing with chi-square test. If you calculated a row frequency or column frequency or something like that incorrectly, I can see if you've shown me your work where you went wrong in your calculations, and I can assess whether you know how to do the process correct and separate that from if you just miskeyed something into your calculator. So my hope is to give those back to you on Monday, and then you'll have that back. What we're doing today is talking about ANOVA. I'm going to spend half of the class period working through the P example with you. I asked you to look at the P example between Wednesday and today. And then the second half of class, there's going to be another faculty member who's going to come in here and do a mid-semester assessment. It's something that they do at James Madison University as a standard practice in all their courses. I'm trying it out this semester for the first time, so about halfway through class there will be a strange woman who walks into class and sits at the back, and then I'll leave and she'll go through an activity with you guys. So let's get through the P's example. So remember that we have these P's that some researcher somewhere inexplicitly fed sugar water as part of the watering regime, and then they look at growth increments. So these are all growth increments. How much did the pea shoot grow over a particular period of time? And I provided you with this graphic that basically shows you what the distribution of the data are in each of these. I don't know what that high-pitched squeal is. Shows you the distribution of the data in all of these different treatments, and it also has the means marked for you, and then it has these lines that show you approximately where the means are. So one of the things that I want you to get across in your head is that the analysis of variance depends on these two fundamental measures of variation: variation among the means and variation within the means. We can calculate what the grand mean is here, which is 61 point something, if we just add up all of these values and divide them by 50. So the grand mean is simply the mean of the jth observation of the ith treatment. So in this case, treatments vary from 1 to I, and there are 5 of them. So I in this case is 5. And observations within treatments vary from 1 to j. And because all of these have the same number of observations, there are 10 observations. We will get 50 observations total. 5 treatments, each treatment with 10 observations. So whenever I write xij, this is the ith treatment, and the jth observation. Now, I'm giving you this terminology because it's going to appear on a slide here in a few minutes. My advice is don't think about these things in this way, but I'm just giving you the notations. So what we do is, this is just how we define which observation we're looking at. It's the second observation in the first treatment. So from that, we subtract it from whatever the mean of the ith treatment is. We square that. We sum that across all of the jth observations and across all of the ith treatments, I from 1 to whatever the number of treatments is, and j from 1 to whatever the number of observations is. This is just mathematically how you would calculate the grand mean. All this says really is, oh, sorry, that's not the grand mean. Sorry. That's the sums of squares total. The grand mean, sorry, let me go back to the grand mean, is the sum of the ith, the jth observation from the ith treatment divided by the grand total of the entire data set. Once you have this, now I've totally screwed you up. Reset. I'm so ingrained in thinking about mean squared. So the grand mean is just add up all of the variables across every observation within every treatment. Add those divided by the total sample size. That gives you the mean. This thing that I was drawing up here basically is the deviation of individual values from the sample mean, added up within each sample, and then added up across all samples. This is sums squares within. This is the within sample variation. Yes?
For the grand total mean,
Yes.
could you do the sums of the sample means divided by the number of samples?
Only if the sample size is equal across all of your samples. So in this case, you could actually just add the mean of sample 1, the mean of sample 2, the mean of sample 3, the mean of sample 4, and the mean of sample 5, and divide that sum of sample means by, in this case, the number of means. But the only reason you can do that is because all of them are the same size. If they're different sizes, you could, so let's say that sample 1 had 8 observations, sample 2 had 10 observations, sample 3 had 12 observations, sample 4 had 5 observations, and sample 5 had 8 observations. You could take this mean, multiply it times 8, plus mean of 2, multiply it times 10, the mean of 3, multiply it times 12, plus the mean of 4, and multiply it times 5, and add that to the mean of 5, and multiply that times 8. And then you would get that sum, but then you would divide it by the total number of observations again. Wow, that's really irritating, isn't it? So generally when we write the grand mean, we write it this way. It's just add up all of the observations regardless of treatment and divide them by the total number of observations in your experiment. This is within sample variation because you're distinguishing the individual values from their sample means. This is why this is sum squared within. Sums of squares among is the treatment means and how they vary from the grand mean squared. So you would sum this across all of the treatments. And so this is sums of squares of how the treatment means differ from the grand mean. And sums of squares total is the sum of the individual differences between the individual values and the grand mean squared, summed once again across all of the values within samples and summed across all treatments. This is the total variation because it's looking at the variation between the individual values and the grand mean, regardless of what treatment you happen to be a part of. So a way of these are the mathematical equations that you use to write these things out if I ever asked you to write them out. Guess what I'm never going to ask you to do?
Thank you.
I'm never going to ask you to write them out. What I want you to know is I want you to know how this works. So the easiest way to do this is graphically. Here's the grand mean. Here's the grand mean. Let's plot it on there. The sum squares total is asking the question, what's the difference between this data point and that? Square that difference. This data point and that. Square that difference. This, that, squared. 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 Plus the difference between this and that squared, this and that squared, this and that squared times 3, this and that squared times 2, this and that squared times 1, this and that squared times 2. Plus the difference between this and that twice, this and that 3 times, this and that twice, this and that twice, plus the difference between this and that squared twice, this and that squared once, this and that squared twice, this and that 3 times, this and that 3 times, this and that 3 times, all those differences squared, different 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 squared. What's the difference between each of the individual values and the grand mean squared, all added up? Total sums of squares. Sums of squares among basically asks, oh, where's my grand mean here? I need my grand mean and all my other means. Right? This is weird. Let's just draw the grand mean on here. The grand mean here was right here. The sums of squares among means isn't the difference between this mean and this mean, it's the difference between this mean and the grand mean, that difference squared, plus the difference between this mean and the grand mean squared, plus the difference between this mean and the grand mean squared, plus the difference between this mean and the grand mean squared, plus the difference between this mean and the grand mean squared. 5 units. You'll have as many means minus grand mean as you have treatments. So there are 5 of them there. That's the sums of squares among. How do each of the sample means differ from the grand mean? Sums of squares within you're already familiar with because you've already calculated this. That's asking within any sample, how does this data point differ from the sample mean squared, this from the sample mean squared, this from 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 sample mean squared times 3, this from sample mean squared once. Do that same operation for this sample and that sample and that sample and that sample and add all of that up. And that's cumulatively the total amount of within sample variation. Doing it graphically this way, you get a sense of what the equations are actually doing. 2 of these equations deal with the grand mean. 1 of these equations deals with the sample mean. The one that deals with the sample mean is the one that is the within sample variation. Questions about how those formulas interact with my shenanigans at the screen? Everybody following? Okay, then let's go through and work it out. These are the formulas. My advice, don't learn this. Learn how to actually operate it, and then you don't ever have to worry about the formulas. this is what a ANOVA table looks like. The degrees of freedom for the among, so for sums of squares among is the number of treatments minus 1. The degrees of freedom within is the number of observations total minus the number of treatments, and then the total is just the total number of observations minus 1. So in this case, we have 5 treatments. So the degrees of freedom for the sum of squares among is 5 minus 1, which should equal 4. The total number of observations, so this is for degrees of freedom among, this would be degrees of freedom within. This would be the sum of all of the, the sum of the ends of all the treatments is 50 minus the number of treatments, which is 5. This would now be 45. 4 and 45 should sum to 49. The total sum of the squares is the total number of observations minus 1, which happens to be 49. So these things are additive. So one of the first things that you should do whenever you see an analysis of variance table is look at the degrees of freedom and see if the degrees of freedom are correct. Degrees of freedom here should be 4. Degrees of freedom here should be 45. 4 and 45 should equal 49. 49 should be the total number of observations minus 1. Total number of observations is 50, so our degrees of freedom match. Sum of squares among is that equation. Sum of squares within is the top equation. The mean squared is just the sum of squares among divided by the degrees of freedom. Once again, the sum of squares within divided by the degrees of freedom within. Sum of squares among plus sum of squares within should equal sum of squares total. Mean squares are not additive, and then the F statistic is the thing that you actually calculate, which is just the variation among means divided by the variation within means. That's the mean squared among divided by the mean squared within. This is what it looks like for a P's example. The first thing that you have to do is you have to get the mean. So in order to get the mean, you have to sum all of the values up, and then you divide them by the number of observations. So 701 is the sum of the control, so that means that when you divide that by 10, you'll get 70.10, 59.3, 58.2, 58, 64.1, because, whoop. I'm unable to advance. Unable to do what I'm trying to do. Has this thing glitchier since they put Apple TV in? This then is the grand mean. The grand mean can either be done, like Grace said, by adding these up and dividing by 5, or it can be done by adding all of these up and dividing by 50.
But you can only add and divide by 5 if
they're this equal sample size.
Otherwise you gotta weight it.
Otherwise, you have to weight it, and if you're going to do all that weighting, you might as well just add the whole thing up and divide by 50.
Okay.
All right. That is just peculiar as can be. So what we're going to do, we're just going to get rid of everything. Just hang with me and don't look ahead. I'm going to go through this stepwise for you, but since the computer is not complying, we'll just go through this. So this is just from a spreadsheet. You can easily do this in any spreadsheet. So you get the sum of the individual observations. You divide that sum by the sample size to get the mean. Your total sample size is 50. Your grand mean is 61.94. What you then do is you essentially subtract the mean from 75, square that difference. So you would take this minus 70.1, square it, minus 70.1, square it, minus 70.1, square it, minus 70.1, square it. et cetera, et cetera, et cetera. You would do that for this treatment. You would do 57 minus 59.3 squared minus 59.3 squared. Do that for that. Sum across this thing, it would give you the sum of squares within here. Sum across this, it would give you the sum of squares within here. Do that across this, across this, across this. You get each of these sums of squares, and then you would add all of those up, and that would give you the sums of squares within. That's essentially basically doing this. What's the difference of the individual values from the sample mean squared, added up across all the observations within a sample, and added up across all samples. This is the thing that goes in to these sums of squares within part down here in the ANOVA table. Then what you would do to get the sums of squares among, you simply take 70.1 minus the grand mean, 61.94 squared, which should give you 66.59. You would take, or you could do it also, 70.1 minus 61.94 squared plus 59.3 minus 61.94 squared plus 58.2, the mean, minus 61.94 squared, et cetera, et cetera. That's 66.59, 6.97, 13.99. Your sum squares among is 1,077.32. That figure goes down here in the sums of squares among.
But where'd the 1077? That's not a simple sum across.
It's not a simple sum across because each of these is then weighted by sample size. So you would multiply each of these times 10 in this case, or you would multiply it times their various sample sizes if sample sizes were unequal. So this would be 600. No, that is not correct either. What am I doing wrong?
Just 107.
It's the sum of all those times 10.
Is it the sum of those times 10?
Yeah, that's what it would be.
Okay, it's the sum of those times 10. That's what it is.
Why do you times 10 though?
Once again, it's a sample size issue, and I just. And this would be a weighted sample size if you went through and had different sample sizes. So I'll check that and make sure that that's correct, but that's looks like what it's doing, and I just had a brain fart right there. Ultimately, that gives you, assuming that this will show up. Oh yeah. That is your sum squares among. You would divide sum squares among by 4 to give you the mean squared. Divide sum squares within divided by the degrees of freedom to give you 5.46. this divided by that is f. In this case, an f of 49.37 is extremely big. And as f gets large, you tend to go towards significance. And in this case, the p-value is really, really tiny. It's less than 1.0 times 10 to the minus 6, indicating that at least one of these means is different from one of the other means. And we already know that because we've already gone through and kind of graphed it so that you can see that this mean is different from all the other means, this mean is different from the remainder of the means, and those other means are not different from one another. This mathematical operation that we've just gone through is just demonstrating to us a numerical answer for, are these things different from one another? Yeah.
Sorry, I missed when you were explaining why you multiplied it by 10.
It's just counting for sample size. In the same way as we accounted for sample size down here, you weight everything by the sample size. Since these are all the same sample size, n equals 10, it's a simple calculation of what that sample size is. If you had different sample sizes, those would once again be an average across all the sample sizes. You've just operated by hand your first analysis of variance. Easy enough to do when you only have 5 treatments with 10 observations in each one. We're going to do bigger data sets that will work out by computer. But before we do that, we will, next time I see you, work through an example that has varying sample sizes, and we'll go through the same calculations. So over the weekend, if you want to take a shot at a variable data set, these are the sizes of ticks found on different hosts, and at the very least you can get the means, the sample sizes and some squares within, as well as the total sums of squares if you want to do that. If you have the sum squares within and the total sum squares, what can you do simply by subtracting some squares within from some squares total?
Some square amount.
It'll give you some squares among. So that's always a way that you can go and check your math. So, yeah, Matt.
So do we not have to do like the sums of squares among divided by the sum of squares within?
Yeah, that's what. No, you don't ever do that. And that's why I didn't say sums of squares here. It's variation
Okay.
among means divided by variation within means. Because what is this when you divide by n minus 1 in a single sample? It's just a variance estimate.
Okay.
So these are actually just the numerators of different kinds of variance. And when you divide that numerator by the degrees of freedom, you go from having the sums of squares to actually having the variance. When I first put these up here, you saw me write variance among means and variance within means. I changed it to variation to make it more general, but it literally is variance. It's a variance estimate.
Okay.
Sums of squares divided by degrees of freedom, that always gives you a variance. Yep. So you never divide sums of squares by sums of squares. You always divide mean squares by mean squares. All right. It's Dr. Judy Diltz. She is going to take you through the activity I told you about earlier. And
Warn them, huh?
I give them a small warning that we weren't going to be spending all day on analysis of variance.
And I know they were sad.
I'm sure they were. And we're missing 3 students?
Yeah.
Yeah. Yeah, we're missing 3 people because of sports. Yeah, that's correct. All right, I'll leave you to it.
Thankful.
Sure.
Um,